Got it. Hello. We're going to do some Sunday morning science. I've got some cryogens that I'm going to mess around with today. All right, here's my setup. First thing we're going to use is some good old dry ice. Minus 109 degrees Fahrenheit, negative 78 Celsius. I'm going to get some of this in this plastic baggie here. We're going to watch what happens. Hold on, I got to get my hammer. Where's my hammer? Did I not bring my hammer? There it is. All right. I'm going to put a little bit in the baggie. And, hello, folks. Okay. I'm going to just pop a little bit of this dry ice into this baggie. I hope it doesn't break. There we go. Oh, hit the camera, of course. There we go. Now let's just crunch it up like that. That'll make it so it can get energy more quickly. The dry ice will get energy from the bricks it's laying on. And dry ice is solid carbon dioxide. And when it warms up, of course, at room temperature, carbon dioxide's a gas. So we're just going to watch what happens. Yeah, it is dry ice. Yep, solid carbon dioxide. I'm going to try to warm it up. Notice the baggie started flat. And you might already notice it's starting to fill up the bag a little bit. Yep. I'm going to try to move it around so I can warm it. The quicker it warms, the quicker the bag should inflate. You can see it happening. It's like a little pillow now. I want to make sure I have a good seal here. Let's make sure I got a good seal. All right, so as that dry ice warms, the solid carbon dioxide is going to go to a gas. And you can see the plastic baggie's filling up with carbon dioxide gas. Next, what I'm going to do, hey, welcome from folks in Canada and India. You don't want to see my lab. You really don't want to see my lab this time of year. It is a mess. Next thing I'm going to do, though, is I'm going to take this baggie full of carbon dioxide gas, and we're going to pop it in some liquid nitrogen and see what happens. Well, hold on, I got to get some liquid nitrogen. You can watch your baggie fill up. Hopefully it won't pop. All right. Let's get our liquid nitrogen. Let's see. We'll look over here. Here's my tank of liquid nitrogen. And we'll fill a little cup with some liquid nitrogen. Let me get my protective gloves. All right. I know a lot of folks say I shouldn't be using gloves with liquid nitrogen, but these are specifically designed for use with liquid nitrogen. All right, let's get some of this stuff poured out. Here we go. Oh man, the bag's about ready to pop. Oh, I better hurry. There we go, got some liquid nitrogen. Yeah, look at it, check out the bag. That thing's about ready to go. Oh, I don't know if it's gonna get in the nitrogen in time. I better start cooling it down. I gotta get a bowl. Here we go. Here's a bowl. Oh, that's gonna blow. Man, is that gonna blow. Let's get it in some liquid nitrogen as soon as we can. And liquid nitrogen is negative 321 degrees Fahrenheit. That's more than cold enough to, let's try it this way, cause, you can see it happening down there at the bottom. It's recrystallizing. So the carbon dioxide gas that's in this bag is now being chilled way below the temperature where it solidifies. If I can, it's really bad that the styrofoam bowl is the same container as the dry ice. But if I get it like this, sometimes you can see it. Let me fill it up just a bit more. It's kind of cool to see. There we go. All right, so let's take this baggie. Let's see, oh, I just can't quite get it topped off enough. There we go. There we go. Now you can see the carbon dioxide is going back to solid when it's placed in the liquid nitrogen. Let's see if we can pull it out and watch. Yeah, you can totally see the baggie is starting to decrease in size, but the carbon dioxide is not going anywhere. It's just recrystallizing into a solid. Look at that, see it? Because it's, you know, in the liquid nitrogen, nitrogen's way colder than the temperature at which carbon dioxide solidifies. Isn't that cool? By the way, I can do this with my hand because the bag is, the gas in there is insulating my hand from any cold. Look at that. Hey, let's just stick it here on the brick and see what happens as the solid warms. The solid carbon dioxide, as that warms, it should go back to a gas, right? Yeah, carbon dioxide is a really curious material. It does not exist as a liquid at normal atmospheric pressure. So it's either a solid or a gas. You can see we've made solid carbon dioxide by taking the gaseous CO2 in this bag and cooling it to well below the temperature at which carbon dioxide forms a solid. So yeah, we're messing around with some cryogens today. Isn't that cool? I thought I'd do a few more experiments with the carbon dioxide as well. We're just gonna let that baggie reinflate. Of course, it's almost pretty full. I bet that thing's gonna pop. It is a bit blurry. I apologize for that. It's from the condensation of water vapor on the baggie. Yeah, that's a little better. And that's going to, oh, but yeah, that bag's really getting tight. Might as well let it see if it'll pop, huh? Let's just see if that baby pops. We'll let her go. That's really getting tight. Look at that. Oh, we'll turn it around the other side so it'll warm a little quicker. Man, that's really, really getting tight. Dry ice expanding in the bag. That is really tight. That's going to go any moment now. We'll back it up just a bit so we can see a little better. And while that's happening, I'm going to try to get another experiment going with some dry ice for you. Tell me, I'll know when it blows. Let's see, get some universal indicator. Let's get some acid and base. I got my dry ice. That's still not popping. Wonder why. I guess you really got to get a bunch of... Let me turn it over the other side, get her warming again. Oh, is it going to go? Is it going to go? Yeah, it's going to evaporate quicker in a warmer temperature for sure. That's why I keep flipping it over, because it cools the bag and then doesn't sublime as quickly. Man, look at how tight that thing is. That's going to go any second. Flip it again. Look at how tight that is. Oh, man. CO2 subliming in a bag. Round and round it goes. When it pops, nobody knows. put it under a blowtorch. Well, I got one in my lab, but I think that would probably make the melt the bag before it popped the other way. Man, that's just not going. Let me get this other thing set up here. Let's get the other thing set up here. A little dry ice in some water. Well, it's not like a pillow anymore. It's really, I wouldn't want to use that for a pillow. That's too tight. Plus, it would probably hurt my ears when it finally went. Man. Maybe, here, let's try some warm water. Let's do that. Let's do that. I'll get some water, pop it in a bowl. That'll help it. Continual supply of energy from water in a bowl. That'll probably do it. Hello, Darshan. In goes some water. All right. Maybe the bag's just going to hold. Pop it here. Stick it in. There we go. We're getting some contact now. If this does do it, man, look at that. Does laser light bend in carbon dioxide because it's heavier density like sugar dissolved in water? That's a good question. That's a real good question. I guess I could get one of my lasers and try to shine it through here. That is just not going. That is just not going. I'm going to reverse it. Might as well. Because that's an experiment. Oh, there it went. There it went, baby. There we go. Finally. Man, that took forever. Did it cause the... Yeah, look at that. The bag ripped. Look at that. It blew a hole right in the bag. Pretty cool. Here, I want to show you another way that we can do that same experiment. So let's get this water out of here. And the idea, remember, is that carbon dioxide is normally a gas at room temperature. So I got a little piece of dry ice here. So, you know, this piece of dry ice is minus 78 degrees Celsius. And obviously it's warming as, you know, the air hits it or as it sits on the block. It's going to gain energy from the block. And the carbon dioxide, it doesn't melt. It goes directly from a solid to a gas. We call that sublimation. I imagine most folks who are watching my channel know this. Yeah, so at normal temperature, carbon dioxide's a gas. But if you can get it cold enough, you know, below 78.5 Celsius, it'll form a solid. And you can do this using liquid nitrogen. So what I'm going to do here is I'm going to get a dewar, put some liquid nitrogen in it. And this is a special dewar because we can see through it. Thanks, Castro. All right. So hold on. I'm getting my my dewar here. I'm taking I'm not really supposed to do this, but I'm going to take this coat off so you guys can see what's going on. All right, so that's a special dewar so we can see inside. We can watch what's going on inside the container. Let me get this just a little lower so we can see just a bit better. All right, now I'm going to pour some nitrogen in here. And it's going to boil rapidly as first. As the nitrogen cools the dewar to 77 Kelvin. What is that, like minus 196 Celsius? Something like that. It's down there. It is down there. It's cold enough, though, to cause carbon dioxide to go to a solid. I got to pour a little more in here. So here's some more nitrogen going in. More nitrogen going in. It's going to be angry at first, boiling like crazy. As it cools the dewar to the same temperature as the nitrogen, 77 Kelvin. Can I use liquid nitrogen to freeze carbon dioxide back to a solid after the sublimation of it? Yep, that's what we're doing. That's exactly what we're doing. Hang on there, baby. All right, so you can tell now that the nitrogen is no longer boiling rapidly because, it's chilled the inside of this dewar to, roughly the same temperature as the nitrogen itself. I'll pour some fresh stuff in just to get us a little more. And see, the deal is here, that nitrogen is, evaporating, and it's forming a layer of cold nitrogen, like right up in here. All the way, but right about here, there's going to be a really cold layer of nitrogen. Very cold. And I am suggesting that it's cold enough to cause carbon dioxide to go back to a solid. Here's how I know this. I'm going to take my dry ice, which you see in the air, right? See in the air? Oh, I can already see it happening. In the air, we see some stuff coming off. This stuff coming off is water vapor that's in the air that condenses on the cold carbon dioxide and forms little clouds of water. But if we do the same thing in here, remember, this is going to a gas. And if I cool that gas to liquid nitrogen temperatures, it should form a solid. And what we'll be able to see it happening? Right in there. Sure enough. See that little cloud I just made? What do you think that cloud's made of? It's not water. That's a cloud that we're seeing right on top of the layer of nitrogen, right up here. That cloud is made of solid carbon dioxide. It's a solid CO2 cloud. You can see it right through there. Because the carbon dioxide, as it sublimes, of course, first sublimes and then gets chilled in the nitrogen and forms CO2 solid, CO2 ice. So we're seeing a little layer of a cloud right there form from carbon dioxide. It's kind of cool, eh? Yep, that's right, CO2. You can also see some of it's actually going into the nitrogen. You can see that this is not as transparent as it used to be. And that's because some of the carbon dioxide ends up falling into the nitrogen. And, now there's solid ice particles of CO2 dissolved into the nitrogen, little icy particles. The more I do it, the whiter I should suppose. There's my cloud again. Now if I pop it down in there, and it really goes. So what the heck's going on there, right? As soon as I pop it in, all of a sudden it just goes like crazy. What's happening there? Well, I know this is cold, but to the liquid nitrogen, this is incredibly warm. This is like fire hot to the nitrogen. And so when I place this into the nitrogen, it's like putting hot steel in water. It causes the nitrogen to boil like crazy. So the nitrogen boils like crazy, pushes against the CO2, and some of that, comes off and boils a little more. We got a really nice CO2 ice cloud going on here. Very nice. Hey, Ed 8, welcome. Thanks for your suggestion, inspiring couple videos here. Let me blow it off. That doesn't work real well because, of course, my breath contains a lot of gases that are both going to solidify and condense in the cold liquid nitrogen. So I'm going to try to just scoop it out as well. Maybe we can try watching that again. It's getting a little tough to see. This happens. This happens with this experiment. Pop it down in there again, touch it to the nitrogen, boils rapidly, And there's your CO2 cloud. That's a cloud made of little tiny ice particles of carbon dioxide. Isn't that beautiful? Very beautiful. Of course, now I've ruined all this nitrogen. It's got a bunch of CO2 ice in it. That's not coming out. It's just too cold, right? Just way too cold. All right. Let me just pour it out here because I can use this for other experiments. I don't want to pour that back in with my fresh nitrogen, no. You can see got a little layer around here. That's probably carbon dioxide ice. Let me just touch it here and see what happens. Sure enough, that's going to take it right off. All right, let's pop some carbon dioxide into, well, let me do this first. This is kind of fun. Let me cut off the lights here. I like doing this experiment. I mean, if we're playing with cryogens, let's play with some cryogens here today. Cut off the lights. All right. Focus in a little better. Why is he cutting off the lights? Because we are going to mess around with some LEDs. Let's get them going. Here's LED number 1. Boop. Here's LED number 2. Well, that one's dead. Probably because I stuck it in nitrogen too many times. Here's LED number 2. There we go. Here's LED number 3. And we're going to cool these to different extents. All right? We're going to cool these LEDs to different extents. First one, let's just pop it on some dry ice. Just pop it like that, see what happens. Yeah? The next one, I'm going to put in some liquid nitrogen. So let me get a little bowl ready over here. Bowl of liquid nitrogen so I can pop it in there. And of course, we've got to leave the other one out as our control. Let's see how I can do this best. I think I'll move this back here like this. Pop the nitrogen in. There we go. That stuff's... So this is getting cooled now. That's at like Celsius, negative 78 Celsius. Of course, this is like 20 Celsius. Well, probably a little colder because it's next to the dry ice. This is negative 196 Celsius. I'm going to pop this down in there. Just the... And let me get it up a little higher so you can see this just a bit. That'll be better to see that way. There we go. All right, here we go. You know, I wonder what color the rainbow tea lights would form. I've not seen rainbow tea lights. That sounds like fun. So long, Thomas. Okay. Takes a bit. But at some point, we should start to see... Well, I can already see a slight color shift in this one, but it's not that noticeable. Let me see if we can get it in this back one. There we go. It's getting close. Getting close. Interesting. That's taking a lot longer than I'm used to. You know, I'm going to take this glove off. I've got a little better feel here. There we go. I'm starting to see the shift. There it goes. Come on, baby. Come on, baby. Keep getting cold. Keep getting cold. Colder, colder, colder. Come on. Almost there. Whew, man, that's cold. I need some tongs. Yeah, I'll use these good gloves. So what's going on with the LEDs? They have a band gap that exists between what we call the conductive band and the valence band in the LED. Geez, I'm having a hard time. And that that band gap is associated with a certain energy. And as electrons are promoted across the diode, a photon gets released, and that photon's energy matches the difference in energy in the band gap. And by changing the temperature of the LED, you can change the energy of that band gap. And because colors of light are associated with certain energies, there it is, you can get a different color of light because you've got a different band gap energy. You see the green? Isn't that cool? I've been in chemistry since the 1980s. That's how long I've been there. Isn't that beautiful? So again, how this happens is by chilling the LED, we're changing the band gap energy between the conduction band and the valence band. And because the energy of that gap is associated with, a certain energy, certain photons of light have energies. And so as we change the band gap, we're just going to change the color of light that the LED emits. And obviously, CO2 is not cold enough to do it. We really got to get this cold to see this effect. This is sort of a demonstration of just how much colder liquid nitrogen is than dry ice. So liquid nitrogen is like 100 degrees Celsius, over 100 degrees Celsius, lower in temperature than carbon dioxide, dry ice. Isn't that cool? That's a fun experiment to do. I always like doing that one when I can. Very, very beautiful experiments. So yeah, playing around with some cryogens today. Here's another one I like to do. Let me pour this off to the side. We'll do some more with the dry ice. So this one, we're going to play with dry ice and water. I probably should get a white background for this. It's going to look nicer. Because we're going to see some color changes here. I hope so. Pop that there like that. Get the light back on. See if I can't get a white background here. See some nice color changes. Get these out of the way. I'll put these over here so we can still see them, huh? Still see what's going on with those. Do this. Nice white background. You can see some color better. Nice. All right. Is CO2 conductive? That's a real good question. I don't know. Chem teacher Phil. Yeah, I love his stuff. He does a lot of interesting stuff. Chem teacher Phil sure does. If you guys aren't familiar with his channel, be sure to check it out. This is just liquid water. That's all that is, okay? Sure, y'all let Chem teacher Phil know. I'd love to do something with him. Okay. Now what I'm going to do is I'm going to add some universal indicator to this flask. Here's a pH scale associated with universal indicator. So try to remember that pH 7 is neutral. Below pH 7, that's acidic. Above pH 7, that's going to be basic. I'll just pop that right there for reference for you. We're going to add some universal indicator to this container here. And it goes. Let's give it a second squirt. And that water's looking right around neutral. A little basic. It's a little basic probably because I didn't wash out all the soap. And so my graduated cylinder is just like a little bit basic. But what I'm going to do now is I'm going to pop in a piece of dry ice. Just a small piece of dry ice. We're going to watch what happens. There we go. There goes my dry ice. There it is. And it goes. And let's see what happens. Look at that color shift. Holy cow. We went to acidic pretty doggone quick, didn't we? Look at that. Just from putting dry ice in there. Isn't that cool? So yeah, this is what happens when dry ice gets bubbled into water. It forms acid. I'm surprised it's actually gone that low. I usually don't see it get quite so red. What's fun about this is I can add some base to neutralize it as it's going on. So I'm going to add drops of sodium hydroxide. You can see I've neutralized the acid, but as the CO2 continues to bubble through the solution, it neutralizes the added base and pulls it back to an acidic pH. You can almost see that starting to turn orange. Here we go. Let's try again. I'm going to add 2 drops. 1, 2. All the way to pH 10. Slowly heading back down to pH 6. What's remarkable about that is the pH scale is a logarithmic scale. So as we're seeing a change from pH 10 to pH 6, that's 4 units. Because it's logarithmic, that's 10 to the 4th. So that's a change in 10,000 in the acidity of the solution. 3 drops. There's 3 drops. And back it goes. And if I want to get it a little more acidic than this, I can add some sulfuric acid. Get it going nice and red. Isn't that interesting? You know, I don't know what's going on there. I don't know why. What in the heck is neutralizing the sulfuric acid? There we go. Probably I got a buffer going on is what's happening. Yep. If I've got CO2 in there, we've got the bicarbonate buffering system. So yeah, let's add a little base now. I've got a recent video out where I do some experiments with this. I call it the rainbow tornado. This is more like rainbow fog, I suppose. Hello and welcome. Hello and welcome. Yep. Thank you, Raheel. Buffer action probably with the CO2 is what you're thinking too, yeah? Probably. It looks like I'm gonna need to add another piece of dry ice. And it goes. It's probably getting cold too. A little bit. In goes another piece. Boom. That's almost overflowing now. How long's that gonna take? Let's move this out of the way. I bet we can see some different colors on the bottom. Isn't that cool? I should have my light too. I bet that'll make it look nicer. That'll make it look a lot nicer. Hold on a second. Find my light. Where'd I put my light? There it is. A little bit of backlighting never hurt. That looks cool. There we go. That's going to look much nicer. That's what we want to do. That's going to look much better. Little trick. Yeah, that backlighting helps, eh? Hey, thanks, Isfara. That's really nice of you. Yep, does look better. Add a little base. Let's see what happens with the lighting. 1, 2, 3 drops. Look at that. Come on, baby. That's beautiful. So yeah, this is a little trick. My kids are actually in film, and they teach me all sorts of tricks about how to make things look a little bit better. So backlighting is something that you're going to want to use sometimes. Man, that's really taking it away quick. I got to try to get it in there. Come on, let's see some purple. Let's see some purple. Yep, we got some purple. And then over time, it slowly heads back. Well, it's taking a bit. I added quite enough. Let's see how long that takes. We're stuck at aqua. We are stuck at pH 8. Oh, there we go. Now we're heading down to neutral. Nice green color. And the yellow should be not far behind. Try a little acid. Yeah, that's cool. We do got a buffer going on. It's buffering the acid that I'm adding. That's crazy. I mean, this is 50% sulfuric. Drops of 50% I'm dropping here. So that's, you know, this ain't weak. There we go. Come on, get a red. Look at that. Now we're at orange. What, pH 3 or excuse me, pH 5. Try to get her down to pH 3 or so. Oh yeah, look at that. As I'm adding the acid, you can start to see effervescence. That's probably from the bicarbonate that's been formed, right? Absolutely. You can see it up here at the top. That's totally what's happening there. I've never seen this before. Look at that. That can't be right. Maybe well, no, I don't know what else it could be. I have no idea what else it could be. Oh, that's going to overflow. We better make this basic. I don't want this to overflow. That's cool. That is cool. So as I add the base, should we see that effervescence slow down? It's still quite acidic here. Let's get it in there. Look at that. Sure enough. Man, that was cool. All right, I'm gonna add a little bit of acid again. If I see that effervescence again, I'm gonna guess that that's from the bicarbonate that's formed as the CO2 dissolves in. Let's see, here we go. Let's get it acidic and see what happens. I don't see it. Oh, here it goes. Here it goes. See it? There it goes. Totally what's happening. I love it when I make new discoveries in demonstrations. That's a really, really interesting effect that I've never seen before. Very cool. Very cool. Yeah, as long as you get the pH low enough. Let's really get it lower and see if the effervescence goes even higher. Sure enough, I have it. You can see it all the way through. I can see the bubbles. I don't know if y'all can. Let's see if I can get in closer. See those bubbles there? Yeah, sure enough. I don't see that at the high pH. You know, you got to remember that you're seeing changes in color because as carbon dioxide bubbles into the solution, it forms. No, it does not smell sulfuric. As carbon dioxide bubbles into solutions, it's adding an acid. So try to keep that in mind. Let's add some CO2 to keep our bubbler going. I wonder if the temperature has something to do with it too. I wonder. All right, I'm adding base now. I'll back it back out. There we go. I still see effervescence. Add the base. We should get to the point where no more protons are available to react with the bicarbonate that's present. And the effervescence should stop. Still there a little bit. We are at a low pH. And there it goes. It clears up. I don't see bubbles anymore. Ha! That's cool. That's cool. Okay, as far what I think is going on here is let me draw it over here on the board. All right, hold on. Where's my eraser? This is my guess. I think it's as good as any guess, though. All right. Sorry, this is going to be a little messy over here. Okay. So, let me see. CO2 gas. Let's see if you can see that. Yep. Let's make it look a little nicer. CO2 gas. Yeah, you can see that. Plus water. So as the CO2 bubbles into the water, it forms, we got plenty of room, bicarbonate ions and protons. Is that right? Yeah, but why in the world? Okay, so yeah, so these are present. These are going to be present. Depending on the pH, this is going to become more prevalent, or this is going to become more prevalent, or the other one that could become more prevalent is carbonate. Both of these, when they're dissolved in solution, they'll react with available protons. And if there's a bunch of available protons, let's write it as a principle of the Chatelier here, like this. CO2, I'm working this out in my head as I'm going here. Let's see, CO2 gas plus water reversibly goes to protons and bicarbonate. See if you can see that. Yes, we can. So as you get CO2 bubbling into the water, you're going to make protons, you're going to make bicarbonate. As you increase the concentration of protons, that's going to happen at your low pH. So when you see it turning red, there's going to be a lot of these available. And in chemistry, when we have sort of a reversible equation like this, we know that when we increase something on one side, it forces the reaction in the opposite direction. So as the pH drops, that bicarbonate, I believe, is forming CO2 bubbles that we see come out of solution. Then as I increase the pH, that causes this to drop, and the dissolved CO2 gets forced in this direction. So if this rises, it goes this way. If this falls, it goes this way. So at high pH, you're going to see the bubbles cease because this is going to react with water to go to bicarbonate and protons. At low pH, you're going to have a lot of these around, which is going to force the bicarbonate to form CO2 bubbles. That's what I think is happening. So let's look back here. And that pH is going to have to be, this is pH 6. We got to get lower than that to see bubbles. So if I add a bunch of sulfuric acid right now, that should increase the available protons. And we should see some bubbles. Let's see. Why are your beakers breaking? Maybe you're using, did you see my last video? All right, here we go. Get it in there. Let's see if we see some bubbles. Nothing yet. Get down in there. Let's see. I don't see. I just start to see just a few, but not as many when it's bubbling through rapidly. Interesting. Let me shake it up just a bit. Or let me lower the pH just a bit more by adding even more acid. Get it in there like crazy. What the heck? It's working when it's bubbling fast, but not when it's just resting like this. Let me put some of the more chunk of CO2 in there and see what we get. That's weird. I don't have this entirely figured out for sure. That's too big. That's going to overflow. All right, let's try this piece here. And it goes, and there's the effervescence immediately. What the heck? Why is that where we're going to put the solid in? Yeah, you see that? At low pH, when you got the CO2 bubbling through, we got a lot of bubbles forming. You can even see the effervescence up here. You can see the foam. I got to stop that. It's going to overflow, so let me lower the pH, raise the pH so that I can stop the bubbling. Come on, baby. Man, that's taking a lot of base. I love how you can just sort of see the base get caught in the foam. Did I get it? It's still bubbling. You go a little more. That should take care of it. I still see a little bit of effervescence. Nucleation definitely could be playing a role. What's interesting, though, I think you'll notice, Fridge, as I'm adding, we get to around pH 6, once the system sort of comes to equilibrium, it sure seems like at pH 6, not even the nucleation will work. Hey, let's try it. Let me just throw another piece of dry ice in, right? See if we're going to test the nucleation. Well, I do think nucleation plays a role. I guess what I'm testing now is just to see if we're only getting the bubbling at lower pH, which is what I do think's happening. But it only seems to be occurring when the dry ice is in there. This is really going to make it go. Let's see. See, I'm really whacking it right now, and I'm not seeing effervescence. Now I'm going to add some acid. And I'll bet we'll get some. I don't see it yet. Now I do. I see a lot of little tiny bubbles due to effervescence. Sorry, I know you probably aren't seeing it. Try to, oh yeah. Oh, totally. You can totally see it up here. I better get some base in there before that overflows. Yeah, that's really effervescing. What will happen if you drink a base? Depends on the base, yeah? Depends on the concentration, the strength. In goes the base. And pretty much away goes the effervescence. That's an interesting... you know what? I'm glad I did these experiments this morning. I learned something new today. I love it when I learn something new. So thank you all for coming out and enjoying the show, because I always love it when I learn something new. So I think that's about it for today. I'll hang out here and see if folks have any questions. I really appreciate you joining in. Let's see. Make a bomb. Go check out some of my other videos. Check out my my video on the bucket launch. Hey, thanks for the suggestion, Fridge. Thanks for just pointing that out and making me think about it. You know, Divyesh, I try to do these some Sunday mornings, but I'm not going to do them every Sunday morning. You know, I have, sometimes I get busy. But I tend to do them, you know, Sunday, Saturday morning. I'm not making a nuclear bomb. I also, I do lives on TikTok quite a bit. Could be that nucleation means more surface area, means more nucleation as a cascade that gets the reaction going. Yeah, that tends to be how nucleation works for sure. Yeah, but I think you and I both agree that we're only seeing it occur at low pH. I mean, I'm not seeing it now. My light's starting to die, so it's getting a little harder to see. Yeah, that's a little better. Let me just add that sulfuric acid. I get that pH low enough, and it should take off. And indeed, I can see the tiny effervescent bubbles now. And we can also see the foam forming at the top. Evidence that we've got, I'm guessing, excess formation of carbon dioxide from dissolved bicarbonate is what I'm guessing. Ah, it's coming out. It's coming out the top. I agree. Fridge, if you do experiments, you definitely got to make sure that you buy some universal indicator, however you can get it. It really makes things fun. Hey, thanks, Hasika. I appreciate it. You know, my TikTok live streams, a bunch of people watch those. Just a ton of people. So that's where I tend to do lives more often. So, hey, folks, I really appreciate you coming out, hanging out, watching some Sunday science with me, teaching me some stuff. And, you know, hopefully I'll see you over on my TikTok channel. That's going to be P-Chem Stud or Tommy Technetium. And we'll see you folks around. I really appreciate you being here. So long.